Hello, everybody, and welcome to video 3 of lecture module 2. We are going to be moving away from unit 2, part 2. We have now formed our protoplanets, or the things that are now becoming our planets. We have all of our early planets, and it's time to start our journey through the solar system. We're going to start at home with the planet Earth. So without further ado, let's go ahead and dive right in. Let me bring up the correct slides. So here we are in video 3 for module 2. We're going to start at home with the Earth, and we want to look at the layers of Earth, and we're going to focus on, in this video, the interior layers. We'll return later to talk about the atmospheric layers of the Earth. How do we actually determine the interior structure of the Earth, which is going to be our standard, how we can actually understand the interior structure of other planets. Also, it's how we can tell that the Earth is differentiated. It gives us a whole bunch of information to know the interior structures. With Earth, we are fortunate enough to live on it, and whether you wanted to call this fortunate or unfortunate, we experience earthquakes, which produce seismic waves, waves that travel throughout the Earth, which give us a way to peer into the inside of the Earth to detect the interior structure of the Earth. So we'll spend a good bit of time talking about seismic waves, earthquake waves, and how they actually give us the interior structure of the Earth. And I want to take a minute just to sit here and marvel in the beauty that is the Earth. This is our home, and yes, this is an astronomy class, and while this video is going to include a good bit of geology, perhaps one of the most geology intensive portions of the class, I do want to approach the Earth from more of an astronomical perspective. I'm going to be walking through sort of the same way we'll go through all of the planets. So I'm going to treat the Earth like a planet. What it looks like, what's on the surface, how does the surface change over time, what we can determine about the interior structure, its magnetic field and its influence on the space around us, the atmosphere, what we can determine about the atmosphere, the layers of the atmosphere. So we'll be going through all of these things with each planet. We just happen to know the most about Earth, so we will talk about it before any of the other planets because it gives us the most information that we can then use to understand the other planets. That is technically called comparative planetology, and we need a good comparison to understand the other planets. And our comparison, the thing we compare everything to, for the terrestrial worlds, is our home terrestrial world, the Earth. Let's go ahead and take a look. There are a lot of numbers on here. You do not have to memorize the numbers. I am going to go through them. You will need to know the interior layers of the Earth from inside out or outside in. If you know them one way, you know the other way. But I always like to give a little bit of context and a little bit of information, a little bit of planetary data. It really does set the context for all the planets. By looking at just the raw planetary data, with the trained planetary science mind, what you are learning in this class, you can actually determine a whole lot about a planet just from the data itself, because physics is the same the universe round. So looking at the bulk numbers gives a whole lot of meaning once you know how to translate it. Let's start with the mass of the Earth. Again, you don't need to memorize this number. For the Earth, how much mass does it have? 5.97 times 10 to the 24th kilograms, which probably came in exactly as I wanted to land. That is a big number. That is a lot of mass. How big is the Earth? When we talk about the size of planets, we usually refer to the radius of a planet, not the diameter of a planet. So what is the radius of the planet? It's the distance from the center of the planet to the surface. The diameter would be from one side through the center to the other, so the radius is half the diameter. And for Earth, that's 6,378 kilometers on average. So right around, you can, if you want to remember a number, 6,400 kilometers is a good number to remember. And now, let's start with what's above the surface. So what's above the surface is, well, let's start on the surface itself. Earth is unique in the solar system, and as far as we know, unique amongst all the planets we know about, in that it has liquid water on its surface. In fact, water covers 71% of Earth's surface, but don't be fooled. Remember, by condensation theory, where the Earth was forming, water ice was not one of the ingredients. Metal and rock was. So the majority of Earth is metal and rock. And you can see this by actually looking at the total volume of water compared to the total volume of Earth. So all of Earth's water, not only the oceans, but the rivers and the lakes that you're used to, and please don't go chase those waterfalls, and all the subsurface water, water locked in the ice caps, things like that, that is only 0.13%, less than 1%, a tenth of a percent of all of Earth's volume. We really don't have that much water if we consider the scenario volumetrically. All that water had to get delivered to the Earth after formation. But there is water on the surface of the Earth. It dominates the surface of the Earth. We also have the continents, which is the landmass. We have an atmosphere, and how big is our atmosphere? Something that we'll return to in a later video. It extends from the surface all the way up to about 100 kilometers is the typical definition of the top of the atmosphere. Of course, it keeps going, it gets thinner and thinner and thinner. That top is defined by what's called the Kármán line. I'll let you read about that if you're curious. We also have extended around the Earth, Earth's magnetic field in the region of space that it influences, its magnetosphere. And every planet that has a magnetic field, we want to talk about its magnetosphere. In fact, the presence of a magnetic field not only allows life to persist here on Earth, so thank you, magical, well, actually, scientific magnetic field, this force field that we have that protects us from the solar wind and keeps everything on Earth alive. And we want to know about that. It's clearly important for the Earth. It is very interesting. It tells us a lot of information whether or not a planet has a magnetic field or not. So what is the focus of this video? The interior layers of the Earth. So let's start outside and move in. I've already talked about all the water on Earth. This is just collectively called the hydrosphere. It's the ocean, rivers, subsurface water, etc. Then we have the crust. So the ocean sits on the crust. And we have two different types of crust on Earth, the outermost layer of Earth. We have what we call continental crust. This is where the continents are. We live on continental crust in North America. And this is typically 30 to 50 kilometers thick. Not very thick at all if you consider the 6,400 kilometer radius. Oceanic crust, the crust that's underneath the oceans, it's on average about 5 kilometers thick, much, much, much thinner. So the Earth's crust is a very, very thin layer. This lowest density silicate rock is only 5 to 50 kilometers thick. Below that, you have a very, very thick layer of denser silicate rock that we call the mantle. And it extends from about 3,500 kilometers from the center to just about the surface, 6,350 kilometers. And then we have the Earth's core. We have the central part of the core, the inner core, that as we call it, that's made out of almost entirely iron, has some nickel in there as well, and it is solid. It extends from 0 to 1,300 kilometers, so from the very center out 1,300 kilometers. Then there's a transition, and since there's a transition, we define the outer core. What is the transition? It goes from solid, and now we have a liquid metal, mostly liquid iron, molten iron, and it extends from 1,300 to 3,500 kilometers. Notice that makes a pretty big core, all the way from 0 to 3,500 kilometers. Over 50% of the distance to the surface is our iron core. So those are all lovely numbers right there, and they're rather specific. How do we know those numbers so well? And that's going to be the subject that we're going to dive into. How do we understand the interior structure of the Earth? Because we have not probed deeper than the crust, ever. The deepest hole we've ever dug is called the Kola Super Deep Borehole. It's about a 9-inch wide hole, straight down. Took years and years and years to dig, and it goes down 12.2 kilometers. It's located in Russia, and that doesn't even get it halfway to the mantle because we're trying to go through continental crust that's thicker. So how do we actually know the interior structure of the Earth? We're going to need a different method. We can't directly sample it. What we need is a different way to sense what's going on in the interior. We're going to have to look for something that's sensitive to the different densities of the interior. Also, just a quick note, dig yourself a 12-kilometer deep hole. Doesn't work out. It got so deep that basically the drill bits were melting, so you couldn't continue. How are you going to deal with that? They took a metal plate, put it over the top. That's it. Okay, so since we can't directly sample it, how do we know the interior structure? How do we know all of these numbers? How do we know that the outer core is liquid, the inner core is solid? How do we know that the core is metal? How do we know the size of the mantle? And what we do is we rely on the fact that we understand waves. Humans are clever. We've developed a good bit of physics. We understand how waves work and how waves behave as they travel through things. And we are going to exploit a certain type of wave called seismic waves. And seismic waves are the waves that happen in an earthquake. So I'll probably bang on my table quite a bit here. If I wanted to generate a seismic wave in my table, everything vibrates. You probably saw the camera shift a little bit, and that was from the seismic waves of me hitting the table. And while there are more seismic waves than the two I'm going to talk about, the two that are important to our story are the seismic P waves and the seismic S waves. So P waves, the P stands for primary waves. The P also stands for pressure waves. So P waves, or primary waves, or pressure waves, I mean 3 times the P. P waves, why are they called the primary waves? They travel the fastest through the Earth. So they're the first to arrive at a monitoring station. A seismometer, we have seismic detection stations. Things that measure seismic waves are called seismometers. These are the first waves that we measure. These P waves, primary waves, pressure waves. Why are they pressure waves? Because they're created by applying a pressure to something. So I just made a pressure wave. Then we have our S waves, or our secondary waves. So the S is for S wave, the S is for secondary wave, the S is for the type of wave it is, a shear wave. And these are the second to arrive at the monitoring station. They travel the slowest of the seismic waves. So we're already seeing that there are some information encoded in how fast these things are traveling. Let's look at these in a little bit of detail. Seismic waves are waves, and as waves, they behave with all the wave properties we've come to know and love. So seismic waves will, and this is going to be the key to how we actually use them, because they are sensing and carrying information about the densities that they're traveling through. And what information are they carrying? How do they carry it? Well, seismic waves will change their speed based on the density of material that they're traveling through. The denser the material, the faster they travel. So sound waves, a type of pressure wave actually, travel slowest in gases, so low density stuff. Then as the density increases, they'll travel faster in liquids, and they'll travel really fast in solids. So the denser an object or denser a material is, the faster the wave will travel. And then seismic waves will also change their direction based on the density. As the density changes, they will change their direction. We've encountered this before. This is the same thing. As a wave travels from one medium to a different medium, it will bend, refraction. So if you constantly change the density, you're constantly changing the medium it's traveling through. So as you go deeper, if the density gets greater, that wave will bend, change its direction. So we see that the speed of the seismic waves travel depends on the density, and their path of travel depends on the density, because they will bend based on the density structure. So now we can see that as we detect the seismic waves, how they arrive and when they arrive is carrying a whole lot of information about the density structures they traveled through, the interior structure of the Earth. So we can use seismic waves as our eyes to look at the interior structure of the Earth. We just need to detect seismic waves, understand how waves travel, and use a little bit of fancy mathematics and human understanding of physics to back out the density structure. I do want to spend a little bit of time with these P waves and S waves, just so you can see a little bit of the differences. So here at the top, I have an example of a P wave, a pressure wave. And a pressure wave is just like whenever I bang the table here, I'm going to hit the table, which is going to push the particles down, which are going to hit the particles next, like just below it. They're going to hit the particles just below it. They're going to hit the particles just below it. Or you can imagine, if you're looking at my screen here, I'm going to hit this rod of material right here, this depiction of material, and you'll have this denser compression part that'll pass through it. It'll be compressed as it moves, the compression will move that way, and then it'll be less dense between it. And you can go from the most compressed to the next most compressed, define that as the wavelength, and there's your pressure wave traveling through this. This is how sound works. So a sound wave is a pressure wave. So being that nature, notice that the motion of the wave is the same as the motion of the particles. So everything is moving that direction, which really is going to dictate how P waves behave. And it gives them a special property. One, it allows them to travel quite fast. So this is why they're the fastest. This by the nature of that their particle motion is the same direction as the wave motion, but it also means that they can travel in solid liquids and gases. I said that sound waves are pressure waves. Clearly sound travels through air, through a gas. You can dive underwater. I'm sure some of you did this as kids. Try to yell at your friend underneath water. You can't understand what they're saying, but you can still hear the sound. And you can yell at people through walls. So it clearly travels through solids as well. S waves, however, are different. S waves are for shear waves. So here's the depiction of a shear wave. Here the wave is traveling this direction. This is similar to most of the waves we've looked at so far. So the wave's traveling that direction, but the particles are just shaking up and down. This is like plucking a guitar string, or hopefully I can demonstrate a shear wave here. So here's a string going to create a wave in it, and you can see that it's vibrating. It moves up and down. So that's an example of a shear wave. The string is moving up and down, but the wave travels that direction. And since the particle motion's perpendicular up and down while the wave motion's the other way, these travel slower, and it gives them a huge limitation. So S waves, this one's important, so pay attention. S waves can only travel through solids. The fact that the particles are moving up and down, if this was a liquid, liquids, particles will slide around one another. That S wave will dissipate. It can't travel through a liquid. In a gas, there's no way you can really get the particle motion up and down and the wave motion that way. So S waves only travel in solids. Keep that. That's going to be an important part of the story. Now let's actually look at these seismic waves. So in all of the rest of the discussion, we're going to have an earthquake that occurs somewhere on Earth. So here's our earthquake. It's the focus of the earthquake. This is where it's taking place. And then we'll have S waves and P waves going throughout the Earth. This depiction right here is a rather great one because you can see a couple of things already. So we will have seismic detectors all around the Earth. We can detect an earthquake that happens on the other side of the world pretty easily. And that allows us to see how these waves are traveling through the interior of the Earth. Notice that the S waves are limited to where we can see them. There's this big shadow region. And then the P waves have a different way of travel, and they can travel through this inner region. We can use these travel paths and how they are traveling through the Earth. And since how they are traveling through the Earth depends on the interior density structure, when we detect them, they have embedded in themselves all the information about the density structure of the Earth, the interior structure of the Earth. Let's actually use this to find the layers of the Earth. So let's start with S waves. And remember, these are the ones that cannot travel through liquids or gases. So here's our earthquake. It happens right here on this point of the Earth. And let's just look to see where we detect S waves. We detect S waves, of course, right by the earthquake. And as we move away from the earthquake, it'll be the same on both sides. I'll go to the right. We detect S waves, S waves, S waves, S waves. As we get about 103 degrees away, don't have to remember that number, but as we move 103 degrees away around the surface of the Earth from where the earthquake happened, all of a sudden the S waves disappear. So on the opposite side of the Earth, we have this huge region where we can detect P waves, but no S waves. So none of our seismic detectors, our seismometers, detect S waves. We have what we call a S wave shadow, as if there is this big thing inside of the Earth that's casting a shadow where we cannot see S waves any longer. And we know that this S wave shadow extends from 103 degrees all the way to this point, and 103 degrees all the way to this point. That's a really interesting piece of evidence. Let's piece everything together and see what this is telling us. So we have the fact that S waves cannot travel through a liquid. We don't expect gases in the center of a terrestrial planet. So let's just consider that they don't travel through liquids. We also see this large and very well measured size of an S wave shadow. It doesn't matter if the earthquake is here or over here or over here. You always have the S wave shadow, and starting at 133 degrees away from it, you will always start the S wave shadow. So it doesn't matter where the earthquake occurs, you always observe an S wave shadow on the opposite side of the earth that's always the same size, as if there's this big symmetrical round thing inside of Earth that's blocking the S waves. Oh, well, if S waves can't travel through a liquid, if we had a core that's made out of liquid, like liquid metal, then the S waves wouldn't be able to travel through it, and we would end up with an S wave shadow. So this is really showing us that our core, or at least part of the core, the outer part of it, has to be liquid. And then we can actually use the size of the S wave shadow to use that to determine that this distance from the core to the surface is 3,500 kilometers. So now we have from the center to here is 3,500 kilometers. We know the size of the core. So the S wave shadow tells us that we have a liquid part of our core, and it gives us the size of the core from the center of the Earth all the way out to 3,500 kilometers. Thank you, S wave shadow. That's really, really powerful information just for measuring earthquakes. Now let's take a look at the P waves, a little bit more subtle here. So P waves can travel through liquids. They can travel through this liquid core, or the outer part. So again, let's put the earthquake right here. And now we're looking at P waves. So we're looking at P waves, and what do we notice? We measure P waves, P waves, P waves, all the way to the same 103 degrees, and then we see no direct P waves. We'll still detect some, but they are not getting there when we expect them. They are not directly arriving there from just traveling straight there. And then from 103 degrees to 142 degrees, again, don't remember those numbers. You don't have to. But those are the numbers we measure. You get no direct P waves, and then, oh, we pick up P waves again. We see them on the opposite side of the Earth. They can travel through that liquid core. And it's symmetric, so we have these two regions from 103 degrees away from the earthquake to 142, where we have a P wave shadow. We don't detect any direct P waves. So what is this telling us? How can we interpret this information to learn about the interior structure of the Earth? All right, so let's go ahead and have a look. As these P waves are traveling, if there is a sharp density boundary, if this P wave is going to travel and go from one medium to a different medium, it's going to significantly bend. It will refract strongly at a sharp density boundary. So this is exactly what we're observing. So if there's a sharp density boundary, this P wave should change its direction, bend, as it travels through this denser material, and then as it exits, it should bend again. So you can trace out all the ways that it would go through, and you would see that given the size of the core, that you'd have this P wave shadow. Not only the size of the core, but a critical part is what is the density, because more dense, more refraction. So the size of this P wave shadow is giving us the density of this core. We can calculate out what that is. It's nearly pure iron with a little bit of nickel mixed into it. So the P wave shadow tells us that Earth has an iron nickel core. But the P wave shadow is not completely devoid. It's not empty of P waves. We see some P waves that are getting in there. They're just not directly arriving. They're arriving later than we expect. They are going through and they are reflecting off of this boundary. They're reflecting off of a boundary somewhere within the core. So the P wave will come down And if there's a boundary within the core, they can reflect off and end up in this P wave shadow indirectly. So we can measure how many there are, their distribution, and that allows us to determine that these P waves are bouncing off of a solid surface, because you will get a reflection, another wave property, when these P waves go from a liquid boundary to a solid boundary. So they will reflect off of that solid boundary and fill out the P wave shadow a little bit. So the fact that we have some non-direct P waves within the P wave shadow tells us that we have the inner part of the core is made out of solid metal. And again, we can use the information about that to determine that its size. It goes from the center to about 1,300 kilometers out. That ends how we determine the interior structure of the Earth. I would just like to thank earthquakes, even though they can be disastrous. They have allowed us to map out the interior structure of the Earth, a powerful process that can be applied to other planetary bodies. And we have. We've left seismometers behind on the moon. Thank you, Apollo astronauts that used moonquakes, and now we know the interior structure of the moon. We have a mission to Mars, the Mars Insight mission, one of the biggest NASA missions going on right now. It is mainly there to be a seismometer to detect Mars quakes, to map out the interior structure of Mars. Hopefully you enjoyed this video. I will see you in the last video, video 4 of lecture module 2, in just a minute.